Bubble walls. The rewrite spreads at almost light speed. So what actually rides on that bubble wall? Not heat, not shrapnel, translation. The wall is a moving boundary in the Higgs field, and every standard model field ties into it. As the interface passes, the vacuum expectation value, the baseline that sets particle masses and interaction strengths, snaps to the new number. Wherever the wall has swept, the constants are updated. Wherever it hasn't, they aren't. There's no gradient you could feel, because feeling relies on the very interactions the wall is rewriting. Inside the bubble, reality runs a slightly different program, or a very different one depending on how the potential shifts. If the new Higgs value is lower, some particles get heavier or lighter. If it's radically altered, certain particles might not even be stable. Mass ratios that were finely tuned by evolution and stellar nucleosynthesis no longer line up. Electrons could be too heavy to bind to protons. Protons could become unstable. The weak force range could expand or shrink. Every bound state you've ever counted on, atoms, molecules, nuclei, relies on a balance of forces that the new vacuum does not promise to preserve. The wall itself is thin on everyday scales. In the thin wall limit, it's set by the microphysics of the potential barrier and surface tension. As it moves, it harvests the stored energy difference between vacua, and that energy goes into the fields at the front, into the wall structure, into excitations, possibly into a spray of new particle quanta permitted by the new rules. But don't picture a shock wave that blasts air. The medium is the fields. Air is just one victim among many, and it only exists on the false vacuum side. The speed is the part that kills warning. In flat space-time and simple models, the wall accelerates toward the speed of light. It can't outrun light inside its own region, but it stays close enough that no alert from ahead will ever beat it. Information about the bubble's approach travels at light speed through the false vacuum. The interface follows at essentially the same speed. Signals you would need to prepare simply can't arrive in time, and preparedness wouldn't mean anything after the transition anyway. What happens to matter caught by the wall? There isn't a dramatic push. Think of it as the rug being swapped under your feet while you stand. The fields you're made of are reparameterized. If atoms have no bound states in the new vacuum, the electron wave functions unbind. If nuclei become unstable, they decay into whatever the new spectrum prefers. If charge assignments or coupling hierarchies change, conservation laws you thought were absolute become bookkeeping in a different ledger. No chemical reaction runs, chemistry as a concept stops mapping to the new ground rules. Meanwhile, star interiors and black holes aren't special refuges. The wall doesn't need cold or vacuum. It needs the field to exist, which it does everywhere. The interface slices through plasmas, degenerate matter, and event horizons exteriors equally. Gravity curves the path, but it doesn't quarantine the rewrite. Even space-time curvature only modifies the local bounce conditions. Once a supercritical bubble exists, the expansion front is robust against medium details because it's driven by the vacuum energy difference, not by material drag. Could the wall stall? Only if the energy difference went to zero across a broad region, or if friction from particle production bled enough energy to halt it. Scenarios model builders examine, but the generic outcome still favors a relativistic front. If anything, particle production at the wall is a signature that would flood the new region with whatever the new vacuum allows. Quanta that quickly relax into that world's ground states. To us, that looks like annihilation. To hypothetical observers born under the new constants, it looks like initial conditions. And outside the bubble, there's no hint. Telescopes can't see its edge because light from the edge can't outrun the edge. There's no cosmic ray precursor, no gravitational wave howl that arrives early. The only way you know is to be rewritten, and that erases the knower. It's the cleanest catastrophe physics has ever offered. No suffering, no chance, no survivors, no memory, a reset that leaves not even a story behind. Why physicists take this seriously? To see why this isn't just a tidy metaphor, we have to watch the numbers run. Take the Higgs quartic coupling, the parameter that shapes the valley's rim, and let renormalization group equations march it to higher energies. You don't guess, you compute. Multi-loop beta functions, careful matching at the top mass scale, threshold corrections in QCD and electroweak sectors. Each step tells you how the Higgs potential bends far above laboratory scales. Do this with today's best inputs, and the critique drifts towards zero and turns negative at some high scale. That's the metastability flag. Now, inputs matter. The Higgs boson mass pins the starting point. The top Yukawa coupling, tied to the top quark mass, drags hardest on the running. The strong coupling, alpha dosally, nudges the flow. Shift anyone by a hair, and the high-scale potential tilts differently. That's why teams sweat definitions. A Monte Carlo top mass isn't the same as a short-distance mass. Translate measurements into a scheme where the renormalization works cleanly, then propagate uncertainties through the loops. When you plot the plane of top Yukawa versus Higgs quartic at the top scale, you get regions, absolute stability, metastability, instability. Our ellipse lands in metastability, hugging the border. Absolute stability isn't excluded, it's just not the central call. The machinery behind that plot isn't hand-wavy. It's 5-loop logarithmic resumations for gauge sectors, 3 and 4 loop threshold matching where needed, electroweak corrections folded in, and consistency checks between 222 and 433 loop truncations. When theorists update the global fit, they report how much each input moves the boundary. The top mass dominates, improve alpha T's, and the Higgs mass, and the band tightens. That's why precise collider measurements, Tevatron legacies, LHC combinations, lattice QCD inputs feed directly into a statement about the universe's long-term mood. If the quartic turns negative, does the sky fall? Not on short clocks. You still need a tunneling calculation. Enter the bounce. In the thin wall picture, you compute an action S bounce for the field's excursion under the barrier. The decay rate per volume per time looks like AEXP minus S bounce, ACSBM, with a prefactor A that codifies fluctuations around the classical path. Gravity tweaks this via the Coleman-de Lucia formalism. Space-time curvature shifts both size and action of the critical bubble. In flat space with our parameters, S bounce is gigantic. Put bluntly, the exponential kills the rate. Integrate that rate over the observable universe and the entire future light cone, and you still get a lifetime that makes black hole evaporation look quick. But there's more bookkeeping. Early universe temperatures could have catalyzed transitions. Thermal fluctuations add to quantum ones, and the hot plasma changes the effective potential. Cosmology checks that box by existing. If the electroweak vacuum were eager to go, inflation, reheating, or later hot epochs were chances. They didn't take. That observation constrains exotic new physics that would destabilize us at accessible scales. It doesn't erase metastability. It says if there's a cliff, it's far out. Now, the sanity checks people ask for. Could colliders push us over? The LHC Safety Assessment Group answered that explicitly. Ultra-high energy cosmic rays have slammed into nuclei in our atmosphere and into denser environments across the cosmos, with center of mass energies exceeding any accelerators. Those collisions have been happening for billions of years on targets vastly larger than Earth. If they could nucleate true vacuum bubbles, the visible universe would already be translated. That's not a loophole, it's a natural experiment with a sample size of galaxies. Add to this formal analyses that compare in-flight cosmic ray heavy ion collisions to accelerator conditions. The verdict remains that nature has run the risk already, repeatedly, without incident. So what keeps the conversation alive? Precision. The line between stability and metastability is thin enough that small shifts in the top mass or alpha D could in principle nudge us across. That's why conferences keep revisiting the phase diagram and why you see on the cusp plots updated with narrower ellipses. The direction doesn't flip with each new paper, it converges. Metastability favored. Absolute stability allowed within uncertainties. Outright instability excluded by the very fact we're here. Meanwhile, theorists explore wildcards. Add heavy states at high scales and the running changes. Some extensions stabilize the potential, others destabilize. Gravity at transplanckian energies could reshape the potential's tail. Black holes have been proposed as seeds that alter decay rates in their vicinity. Follow-ups show the story is subtle, and the generic conclusion in our cold, dilute epic still points to lifetimes, beyond comfortingly huge. Across these variations, one message holds. The standard model alone, with measured inputs, leaves us close to a boundary, but not close in time. That's why physicists take this seriously. It's not drama, it's a precise, uncomfortable observation about where our numbers land. The vacuum either is absolutely stable or lives on grace periods so long they render panic unserious. But grace period isn't rhetoric, It's a calculation tied to masses we can measure and equations we can check, which raises the next practical question. If the clock is that slow, what could ever change the odds in our favor? Or against us? Could we trigger it? Cosmic rays versus colliders versus nature. This is the part people worry about. Are we poking the bear? If a bubble could start anywhere, could smashing particles together here light the match? The short answer draws on the biggest, longest experiment ever run, the universe. Nature has been throwing higher energy rocks than we can build for billions of years. We're late to the party and our fireworks are small. Start with the natural stress test. Ultra-high energy cosmic rays slam into nuclei in our atmosphere with center of mass energies that dwarf the LHC. Those collisions happen not just over Earth, but across stars, nebula, and dense clouds in every galaxy. They've been running since the first magnetic field started slinging particles around, and the sample size is ridiculous. If those impacts could nucleate a critical bubble, the rewrite would have happened long before accelerators were a twinkle. Safety groups formalized that argument. CERN's assessments put it bluntly. Whatever the LHC can do, cosmic rays have already done, at higher energies, on bigger targets, for longer, and the universe has not flipped. More careful versions add nuance. In-flight cosmic ray collisions are not identical to collider events because the center of mass can be moving. But even with those caveats, there's a significant subset of cosmic ray interactions that mimic collider kinematics closely enough to count as trials. Trials nature has run at scale. What about exotic channels, heavy ions, dense bunch crossings, small impact parameters? Anything that sounds rare enough to dodge the cosmic test? Heavy ion colliders recreate brief droplets of quark-gluon plasma, but similar conditions occur in supernova remnants and compact object environments where shock fronts accelerate particles and drive dense interactions. The rarest corner cases are still harvested by the universe's breadth. Different angles, materials, and energies drive billions upon billions of times. If a path to a critical bubble existed at those scales, it's hard to explain the silence. There's also a conceptual guardrail. Bubble nucleation is a field-level process governed by the bounce action, which cares about the shape of the potential barrier at astronomically high scales. Local, hot, messy collisions excite fields, but they don't resculpt the far UV tail of the Higgs potential. The tunneling path isn't punched through by a single shard of energy. It's a non-perturbative slide under the ridge that depends on parameters our machines don't control. That's why the decay rate is quoted as a property of the vacuum, not of a lab. Could gravity change the odds near compact objects? Theorists have explored catalysis by black holes, defects, and strings. Some calculations suggest small black holes might tweak rates in their vicinity. Follow-ups show the effect can suppress as well as enhance, and in our cold, diffuse epoch, it doesn't lift probabilities anywhere close to danger. Crucially, if these seeds mattered, the early universe, far hotter, denser, and friendlier to such objects, was their best shot. We're here. That's a data point that swallows a lot of scary parameter space. Zoom back to accelerators. The LHC's center of mass energy is tiny compared to Planck scale physics, where the Higgs cortex high energy behavior matters most. We're measuring inputs that feed the stability calculation. We're not jamming a crowbar into the potential. Safety reports were reviewed and endorsed by independent committees. The conclusion isn't, we hope, it's nature's already tried harder. Bottom line, we're not pushing a red button. Colliders are flashlights, not detonators. The vacuum's fate is dictated by numbers baked into the field and the long, cold arithmetic of quantum tunneling. Arithmetic that the cosmos has been running loudly and safely since before there were hands to worry. The wildcards, new physics, gravity, and extreme environments. So if colliders aren't the trigger and the vacuum's own math is miserly, what, if anything, could tilt the odds? Start with the simplest lever. Add more physics. The standard model is our best tested kit, but it's probably not complete. Any heavy particle beyond it, even one we'll never produce, can nudge the Higgs potential through loops. Some additions stabilize the high energy. Extra scalars, certain supersymmetric spectra, or threshold effects that bend the quartic back upward before it goes negative. Others yank the curve down, deepening the far valley and shaving the bounce action. That's the quiet power of new physics. You never touch the vacuum directly. You change the running, and the running changes the lifetime. Supersymmetry is the classic stabilizer. In many versions, fermion and boson partners balance radiative corrections, keeping the Higgs quartic positive up to huge scales. Even without Susie, a well-chosen scalar singlet or triplet can steady the brim. Conversely, heavy fermions with strong Higgs couplings can drag the quartic lower, pushing us deeper into metastability. None of these are free moves. They're tuned against collider bounds and cosmology, but the principle stands. The vacuum's fate is a bookkeeping problem, and every unseen term in the ledger matters. Gravity is the other lever, and it refuses to be a spectator at extreme scales. Coleman, DeLucia told us curvature reshapes the bounce. Positive vacuum energy, like the dark energy bath we're sitting in, can either hinder or help decay depending on details of the potential and wall tension. Add higher curvature terms, FR models, quantum gravity corrections, and both the critical size and the action shift. In some analyses of Starobinsky-like gravity, bubbles get bigger and tunneling rates drop. In others, higher power extensions can speed things up. We don't have the final quantum gravity manual. We have maps of how sensitive the process is to the parts we can't yet measure. Then there are seeds. Could an extreme environment locally bend the calculus? People have explored catalysis near defects, cosmic strings, or black holes. A cosmic string's deficit angle distorts geometry and can reshape a bubble, turning it rugby ball shaped and altering the threshold. Tiny black holes, especially if primordial ones ever formed, modify field modes near their horizons and have been proposed as nucleation aids. Follow-up work shows the effect is subtle. Some setups enhance, others suppress. And the killer constraint never changes. If this mattered, the early universe was the trial run. Hotter, denser, seeded with whatever exotica nature allowed, it didn't tip. That observation trims a lot of scary branches. What about thermal help? At high temperature, fields see a different effective potential. Barriers can flatten, and thermal fluctuations can compete with quantum tunneling. That's why people comb reheating, phase transitions, and inflation's tail for danger. The electroweak epoch came and went. Any would-be catapult didn't fire. Inflation itself could have been brutal. Higgs fluctuations in de Sitter space are a known worry, but viable inflationary models thread that needle, or new physics stiffens the potential enough to keep us safe. Again, the cosmos answers by existing. There's also the inverse wildcard. We might be safer than the standard model alone suggests. If the top mass shifts slightly lower in a short-distance scheme, if alpha T inches down, if matching improves, our ellipse could tilt into absolute stability. Or heavy states. We'll only infer indirectly, could lift the quartic at the last minute. Conferences keep tightening those ellipses. On the cusp stays the headline, but the cliff edge moves as the inputs sharpen. Even with all this, most scenarios still point to lifetimes so long they flatten intuition. Gravity tweaks, seeds, exotic couplings, none of them in our cold era yank the exponential into human view. The odds remain stacked toward basically never on any practical clock. That can feel like a shrug. It isn't. It's a measurement-driven boundary on how wild the wildcards are allowed to be. And yet that basically never has a footnote. Quantum tunneling never says zero, only not yet. The vacuum's risk is a background hum that doesn't rise or fall with headlines. If anything changes the odds, it'll come from better numbers or a surprise in the running. A particle we didn't expect, a correction we didn't include. Until then, the plan stays boring. Improve the inputs, test the tails, and remember that the universe has already passed its harshest exams without a crack. What you'd see the day nothing happens, no sirens, no glow on the horizon, the calendar doesn't skip. If a true vacuum bubble is born in your future light cone, the first and last thing that reaches you is the wall itself, moving so close to light speed that no advanced signal can ever get ahead of it. One moment, your neurons pass signals, the next, the Higgs baseline flips, and the interactions that define you no longer exist. There's no time to notice. Experience ends at the interface. From the outside, there's nothing to watch. Telescopes can't catch the edge, because light from the edge can't outrun the edge. No ripple fans out through space, no cosmic aurora crawls across the sky. The front doesn't push air or crack. It rewrites the fields that make air and rock possible. A firing synapse, a beating heart, a silicon clock. Each relies on constants the wall replaces mid-beat. The process isn't pain, it's deletion. Inside the bubble, physics is just different. Maybe only slightly, maybe radically, but there's no continuity of memory across the change. If bound states don't exist under the new parameters, atoms unbind, nuclei dissolve, and composite matter disassembles into whatever quanta the new rules allow. If bound states do exist, but with different masses and couplings, they're not the ones you knew. Either way, there's no bridge for an observer to cross. If the bubble forms light years away, you still don't get a preview. Its edge moves almost as fast as the photons that would announce it, so the most generous warning is a vanishingly small interval. Too short for a retina, a detector, or a processor to register. Point a survey at the same patch of sky for decades and you'll never see a ragged boundary advance. The geometry forbids it. By the time information about the wall leaves the wall has already arrived. There's no shelter. Deep underground buys nothing. Ocean trenches, polar ice, magnetic fields, none matter because the medium being revised is the fields themselves. Stellar cores aren't protected. Event horizons don't quarantine the exterior. The interface slices through plasmas and solids with equal indifference because it's driven by vacuum energy, not by friction with matter. Duck and cover has no domain of applicability. If the bubble never forms within our future light cone, you also won't know. Somewhere else in the universe, some other patch could reset, but causal boundaries keep those stories private forever. You can live an entire species' lifetime in a metastable vacuum and never encounter evidence that it isn't the ground state. The risk is global in principle and hyperlocal in practice. Either total, here and now, or irrelevant, forever. This is the strangest part of the threat. We're wired to imagine cinematic endings: fire, shock, collapse. Vacuum decay refuses spectacle. It offers certainty without sensation. The day it happens, nothing happens. The mug is still warm, the sky is still blue, the sentence is still half said, and then the concepts that made mugs, skies, and sentences coherent are replaced. No countdown, no aftermath, no witness. Other cosmic fates versus vacuum decay. Pick your doom. If false vacuum decay is the hard reset, instant, silent, absolute. The other endings feel almost polite by comparison. They give you a timeline, a texture, even a storyline. Start with the default forecast: heat death. Take the universe we see. Dark energy acting like a cosmological constant. Matter thinning as space expands. Structures that are already bound staying bound. And let time run. What happens isn't a bang or a tear. It's a long budget meeting where free energy gets spent and never replenished. Stars burn through their fuel. The efficient red dwarfs inherit the future and sip for trillions. White dwarfs cool into black dwarfs. Black holes feast slowly, then whisper away by hawking radiation over absurd spans. Everything drifts toward uniformity. It's not drama, it's attrition. The irony is that heat death is the only one that lets you plan. You could imagine civilizations adapting, migrating to cooler gradients, hoarding entropy sinks, stretching computation across longer and longer clocks. It's a story told in engineering, not apocalypse. The ending is still a limit. With no gradients left, engines fail, memory fails, and doing collapses into statistics. But you get eons to try. Now the more theatrical cousin, the big rip. This isn't currently favored by data, but it's the thought experiment that pulls the ends of your intuition apart. If dark energy's equation of state dips below -1 and stays there, its density rises as space expands. Gravity loses not just on large scales, but locally. First clusters unbind, then galaxies, then planetary systems. In the final sliver, molecules and atoms themselves lose their grip as the scale factor's growth hammers every bond. It's a schedule with deadlines. The clock tells you when your orbit fails and when your chemistry ends. Observations keep pushing W close to -1, not below, but the model earns its place in the gallery because it shows how expansion alone could finish the job. Turn the tape the other way and you get the old favorite, the big crunch. In a matter-dominated universe with no persistent acceleration, expansion slows, stops, reverses. Everything that flew apart comes back together. In the simplest versions, temperatures rise, densities climb, and you end where you began. Hot, dense, uniform. It's tidy and so far out of step with the measurements. Supernova surveys, the cosmic microwave background, and baryon acoustic oscillations all point to late time acceleration. To crunch, you'd need dark energy to switch off, or flip sign, or for new physics to intervene. It isn't impossible in principle. It's just not the story current data is telling. Stack these fates next to vacuum decay, and the difference is tone. Heat death is a fade out. The big rip is a countdown. The big crunch is a reversal. False vacuum decay is a trapdoor with no creak. Three of them give you horizons on the future. What changes first, what remains, what slowly disappears. One removes the vocabulary that lets future be a concept, and yet they coexist in the same phase space of possibilities, because they live at different levels of the model. Heat death, rip, and crunch follow the dynamics of expansion, energy content, and equations of state. Vacuum decay is microphysical. It asks what the Higgs potential does at scales far above stars, and whether a deeper valley exists. You can be marching toward heat death perfectly on schedule, while living above a buried trapdoor whose hinge is set by a tunneling rate so small you never hear it. That's the twist most people miss. Metastability doesn't replace heat death, it overlays it. If the decay rate is so tiny that no bubble forms in our future light cone before black holes evaporate, the universe experiences heat death as if the vacuum were true. The hard reset remains a logical possibility with a probability that rounds down to not in any era we care about. But rounding down is a choice about clocks. On an infinite ledger, any non-zero rate accumulates. Given endless time and growing volume, vacuum decay wins a coin flip eventually, even if eventually makes a Google years look like a coffee break. Meanwhile, the others carry their own uncertainties. Heat death assumes dark energy behaves like a constant, and so far it does within tight bounds. The big rip lives in the tails of those bounds and keeps getting squeezed. The crunch demands a turn we don't see. False vacuum decay hangs on inputs to the renormalization group, top mass, Higgs mass, strong coupling, and on what, if anything, lives beyond the standard model. None of these are myths. They're inferences tied to measurements, equations, and the stubborn fact that we've already survived the epochs most likely to trigger surprises. So pick your doom, but pick it honestly. If you want a future to work in, heat death is the canvas. Long slopes, scarce gradients, and time to be clever. If you want spectacle, the rip and the crunch are narrative devices that data keeps benching. If you want the cleanest catastrophe physics can draw, vacuum decay is the no epilogue option. The responsible answer holds both truths at once. We live in a universe that, by every sign, is coasting toward a quiet ending. And we might be doing it on a floor that isn't the basement.